The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
And our next speaker is Bernard Eckholdt. I think you go by BJ, right?
BJ.
And BJ is Manager of Quality Assurance Lafarge in Metairie. I butchered that, no doubt.
Close enough to New Orleans, Metairie. Yeah.
Close enough for a Canadian, right? And Metairie, Louisiana. And he's going to talk to us about mixture proportioning to satisfy specifications. So it should be fairly interesting. And with no further ado, I will turn the floor over to him.
Good morning. Over the course of my 20-plus years in the industry, beginning out with starting design for strength, the industry has evolved. Challenges have been given to us to make concrete into something it never was in the first place. Daryl's already talked about mass concrete, low heats. You know, I'm faced with challenges of applications. Some of the topics I cover are underwater and making concrete more durable for permeability requirements. We've already talked a couple of times about the standard methodology. I'm going to go through it really fast. Going to 211 gives us a basis for design for strength. Gather up the necessary information for aggregate, determine appropriate slumps, all taken from the tables, estimating water demands. Now, if you've got your experience in your market area, you know what your approximate water demands would be. If not, you do go to the table. So being there, as long as I have now, it's gotten pretty easy for estimating water demands. Going to strengths, picking water cement ratio off the tables, calculating powder contents back off the water cement ratio water, using the 6.3.6 to determine the coarse aggregate volumes based on the sand FM, so we've been through this already. Add up all absolute volumes of the known, subtract from 27, the remainder is sand. And this is a basic mix design in the city right now. This is a standard 4,000 PSI, 28-day mix, about 510 pounds of cement, sand, gravel, and water demand down there is about 30-plus gallons to get a 4-inch slump out to 90 minutes in the summertime. This is a plain mix right now. We'd ordinarily have retarder in this. So I'm reading the specification, and I know what it takes to make 4,000 PSI, but an engineer in this community has decided that he's educated himself. He knows now that low water cement ratio is a better basis for design than just strength. So he is going to give us a 4,000 PSI mix, but he's also asking us to provide a 0.40 water cement ratio because he wants crack-free concrete. He's going to be power trialing structural slabs on grade, so we're going to have less than 3% air. Back to that previous mix, my 510 with my typical water demand for 4-inch slump, I'm looking at a 0.50 water cement ratio. All right, so the first new design criteria I have is now we're strictly going to base our design on water cement ratio to satisfy this project specifications because I am going to bid the job. Where to begin? Well, first off, we got a technical question. You know, how to make this mix achieve that 0.40 economically? And then we got a moral question is just how much does that engineer know when he says he wants a 0.40 water cement ratio? What is he expecting to see? We have to be competitive because what's the other guy thinking? Is he going to be legitimate? Is he going to put all that cement in there to get our water cement ratio where it needs to be, or is he going to play with numbers? Strength isn't an issue. So first off, to economize, we would look at a high-range water deucer. So backing off take the cement completely out, starting with that water, we're gonna assume we can still make a 4-inch slump with a .40 with that same water. That may be a cause for concern, but for this scenario, we're just going to go through it. Basically, we take our 255 pounds of water. Now we're back figuring water cement ratio into that value, and it comes up with 636 pounds of poured cement. So going through all the normal design criteria, we would come up with the same aggregate amount. Sand has been calculated. So now we've taken our spec mix. This is something that we would want to bid. We're leaving the high range out for the time being. And my material costs, some round numbers, are about $61 a cubic yard to make that .40 straight cement mix. Going back to the original mix design, it only is 4,000 PSI 28 days. We're looking at $55 a yard. So we've just added $6 a cubic yard to our material costs, and that is the basis for my bid. So now I'm going back to that oral question. Well, being the way I deal with it, I'm just going to go ahead and bid the straight mix and take my lumps. Competitors have in the past used the design criteria of saying, well, okay, it takes 510 pounds of cement to make 4,000 PSI. Let's just back calculate the amount of water. So I've seen cases where a producer will send a mix design to an engineer, 24.5 gallons of water. Now, the engineers, unfortunately, don't have the material background that some of these producers do have, so they'll accept that. They've got beautiful strength results. Everything looks good on paper. Well, I don't get the job unless there's some reason that, like in a particular case down there was a lot of other types of concrete on this job, and the contractor actually hired us. So I learned a lot through having the opportunity to spend a whole bunch of extra money on concrete. The other way is actually to design with a high-range water reducer in there to try to see if you can bring cement contents down, and we did. We brought it down. So now we're at $60.83 because high-range water reducers do cost money also. So real quick to compare, the original 4,000 PSI mix, spec mix, Concrete R Us is out there bidding much lower material costs. And at my best price, I'm only going to be able to achieve this. The long and short of that whole story is the engineer called me up and he wanted to know why did my mix line have so much cement in it. And we were having problems in the field. Concrete was cracking and it would get a terrible finish. We poured in concrete in the middle of summertime at 637 pounds a yard. And I explained to him that that's the amount of cement it took to make the water get concrete out of the truck. And I said, you have a piece of paper and pencil. Let's start doing some math. So we went through the scenario of the .40 water cement ratio versus a strength mix, and I explained to him what it takes to get concrete out of the truck, and he was kind of amazed. And then the one up me with that 510 scenario, he actually told me one of my competitors was using 470 pounds of pure Portland cement and got the water down to 22 gallons a yard. So if anybody's in the ready-mix industry, there's no way you're going to make concrete with 22 gallons of water. That was an improved mix, and they used it. Last part of the story is that engineer agreed to take a risk with me, let me design the mix, and the next two pours on grade in the middle of summertime still, we cut the cement, put Super P in, and the problems went away. He got better finish, and he got his FL numbers all to meet that scenario. So that's been one of the interesting challenges, guys, and ladies, and sometimes we'll see that .35 water cement ratio pop out there for air and train concrete. And that's a real fun one because remember, we still have to finish and place and pump all this concrete. Case two, underwater. Underwater concrete is always going to be a challenge because we can't see what we're doing. We have divers on occasion go down underwater and help get things level, get concrete level. I've even saw one contractor who's pretty innovative. He designed what he called a Cajun bull float. He turned the bull float 90 degrees to the handle and had catwalks across the top of the pour, and he used that with a tape on it. We didn't think about tide changes, but that was his elevation control on the water. It was about a 20-foot deep pour. So pump placements typically are going to be used for this. Primarily trimmings. The Corps of Engineers does require trimming. They don't want to allow just a flat pumping. We want highly flowable concrete because we're not going to be able to have someone there handling that boom, placing it right where it needs to be, so it needs to flow to limit that. You got to keep the tip down in there. So a lot of these challenges. And then, is there a washout test to determine that this concrete really is underwater capable or not? Project, one of the massive gate structures in the city after Katrina. This project was 5,000 yards. This water is 27 feet deep. We're going to put a seal slab in there. So this cofferdam is only supported at the top. There's no horizontal bracing below grade at all. It's just driven in the mud. It's neutral buoyancy, so there's no real pressure on this. But we've got the thing catwalked and supported at the top to keep it open. They've excavated, they've driven piles. So they've just scraped off about the top 2 foot of muck, so that when they do put the concrete down, it was a limestone bed actually put down 6 or 8 inches, just something to support the plastic concrete as it was being placed. Specification says all concrete placed underwater should contain an anti-washout admixture at the manufacturer's recommended dosage. They created a test, CRDC 61, to determine the washout potential of a mix. There's a limit to 8% of the mass of the weight, or the mass of the sample being allowed to wash away. Failing is 9%. Cementitious materials, everyone has ever fooled with any type of underwater application knows the higher the cement factors, the better off you're going to be. The mix has to be sticky. There has to be some sacrificial cement. The volumes of coarse fine aggregate, they found that it flows better as you get closer to 50-50 blends and even beyond. So knowing what we know, we've got 600 pounds. Specification typically allows 33 to 35% ash replacement. Because of the reduction in water the fly ash brings, we're going to be able to bring our water demand down to about 240 pounds or just a little bit under 29 gallons. Underwater, we don't need air, obviously, so we've got these design parameters. Then we get into the picking out the coarse aggregate. We've got total. This goes back to the C211 part, where we're just going through and designing. Now that we've got our knowns to calculate our aggregates. So we're given 7.473 cubic feet of paste, leaving us with the remainder of aggregate. So we calculate out 1596 fine aggregate, then the 1596, and this is a formula I've used for a long time now. It's a great little quickie formula to recalculate one weight of material with an equal volume to another weight of material, and it works. So right here we've got the 1956, 9.762 is where it came out. So going through the math, it proves that it works. So now we have a basic mix design, just off specifications. We don't know if this is going to work or not. So in this case, we have to enlist the admix guys to give us a little bit of background on what dosing of like an anti-washout admixture is viable. So to run 3-point curves and so forth, we've shortcut that circuit and go into well, again, we got the opportunities for either 3/4 inch aggregate or 1 inch, and those we found that they limited to about a 9 to 10 inch. After about 10 inches with those size coarse aggregates, even with a viscosity modifier or anti-washout admixture, they tend to start segregating. So if the application is conducive to a 9 to 10 inch being suitable, then fine, you can design that way. But what we're finding is if you can develop an SCC in your market, it works perfect for underwater applications because the flow is so much better. The contractor saves time. There's fewer vertical pipes have to be installed, and the job goes quicker. So now we've got our basic mix, and now we've added a 10-ounce dose of anti-washout admixture. So we're going to try to see if it works. You know, is that going to be suitable to give us that maximum 8% loss? And this is my good buddy, Mr. Cheek. He has an 8-inch PVC pipe that's about 8 feet tall. There's a little basket in here. It's a plastic basket, and it's got thousands of holes drilled in it. Put your sample in, weigh it, put the lid on, and then drop it down to the bottom and hoist it back up. You do this 3 times, you take loss through the course of the 3 different tests. So any mix you want to run to determine any washout, this is the apparatus that the Corps came up with that is used. So he sends me back a test report saying our 1-inch aggregate mix had a very, very low percent loss. We've got a SEC mix. It's got a little higher, but we're still on the specification. And what we're attributing that to is the little holes in that basket, even though they're small, the high fluidity, the high paste volume of those SEC mixes, a little bit more is allowed to creep out of the holes. And that was proven in the field. And that is the end result. And you can tell what the scale is. The power driven, that little limestone base is under here. We've got 4 feet of self-consolidating steel slab. It was dewatered, and the contractor had a fish fry. When they took the water out of that hole, they had about 250 speckled trout, which down south means a heck of a lot to us. And they had one bodacious fish fry. And it was successful. That was 5,000 cubic yards. That structure is what was called the temporary bypass. Right beside it was the permanent bypass, or the permanent gate opening, and it was a 10,000 yards. So once this contractor, by the way, this is a 1.2 mile wall separated into 3 or 4 different contracts by one general contractor. Once this guy did it and was successful, the other folks that were actually contemplating making a property of twice that size in the dry decided, to heck with that, we'll just go ahead and do this because it worked. Case 3. How's the time? You're doing good. All right. 5 minutes. All right. We're building a petrochemical plant down there, and our specification is coming out with the new 318. Tim touched on it before. 211 doesn't have the exposure categories yet, but it's coming. The 318 does. So some of the design engineers in New Orleans are starting to pick up on the C classes and Ps and so forth. Then 318.08. So we've got the P1 category, and there's also a specification saying we want chloride ion penetrability to be very low, as stated in 1202. And that gives us a coulomb value ranging from 100 to 1,000 coulombs. And it's either 28 or 56 days, depending on how much time they do have to spare. So now we've got a new set of design criteria. It's not only compressor strength or water cement ratio, it's how dense can we make that concrete to protect our reinforcing. So ACI 318 4.3.1 gives a 0.50 for our class P1. So that's just a criteria. So to take the next step into, well, let's not have a trial and error process going on forever, going into 201 durability, we're told that a 0.40 is going to actually be the optimum, which I learned this during this presentation. The 0.40 is the optimum level for cement hydration. Too much above that, obviously we're losing strength. Much below that, and we start leaving a whole lot of unhydrated cement in the mix, which leads to voids and so forth. So if we're at around a 0.40, we've got an optimum cement efficiency of hydration. Also, you break up capillaries by having the efficiency there and not create so much calcium dioxide. See, 6.4.3 mentions SCMs is helpful. So that's it. I've been told now, okay, 0.40 is a good thing to be at, and the SCMs are helpful. So with that, let's look around and see what's available. We do have silica fume. It tops the chart for densifying concrete. But it's expensive, and it's a challenge. We've had projects so big that we actually installed silos specifically to carry silica fume. 200,000 yards will buy a silo. Class F ash, if it's available, as Darrell has shown, Class F ash has better properties than C, except you have that rare C that might actually enhance durability or temperature control better. But we do have access to 2 slags in the market. The GGBFS is brought in by 2 different producers. So the question is, okay, is a 100 going to be better suited for our design, or is it a 120? That's a trial and error process. No real shortcuts to that. It's a material package. You have to test it. So we know we want to maximize our aggregate volume, minimizing our paste content. So we definitely want to use a superior aggregate, not pit run stuff. This one's going to take some substantial quality control on the producer's end. Down south, we have a lot of mom and pops. So for most of the projects down there that we get into this, we're going to buy from the major producers. Those are the better quality control programs. Angular, well graded. We've tested coarse crushed material against round river gravel and found the permeability is better enhanced by using angular materials. Run a theoretical combined aggregate grading curve. Jim went through that, so I'm just going to mention it. If the slag is available, all right, the trial started at 50%. In this case, we started at 50% because that's what the specification actually allowed us. So we just went to the maximum and we worked backwards for a 3-point curve. It's going to take a high-range water reducer to get the water-cement ratio down that low, even with 50% replacement slag. And do we need air? Well, if we're going to have an FO, like we do in our market down in New Orleans, then we're not going to put air in concrete intentionally. It's only going to be if the specification requires it or some other benefit. Obviously, if we design it for free install, we will, but down there we won't. So, to take a mix and run a trial, we've got the water demand of about 240 pounds, back figured at 0.40. We're at 600 pounds total cementitious. We're at 300 and 300 on 50-50. Taking a limestone, and because we do have to place, pump, and finish this mix, we're going to blend in to try to get that combined aggregate grading curve better. So an intermediate pea gravel, leaving us with the 1,289 pounds of sand. And we actually do create this mix with the high-range water reducer somewhere in the range of $65. So it's still a better deal than having to use just straight cement with a much lower water-cement ratio and silica fume. So this is where the economy comes in. The high SEM replacements give us the ability to be much denser. And this is a 56-day result. And our low trial batch has actually gotten us in the very low category. Again, it was a 100 to 1,000. And in this case, it's 56 days. So we meet the very low requirements. Success.
Terrific.
Yes.
Thank you. I think we have time for one.
Okay. Go right ahead.
In the mix designs you show on that the lightweight, but you haven't discussed using the lightweight sand as a replacement of some of the other sand.
Well, I picked these three categories. Like that template back there that you saw, that's my everyday working Excel spreadsheet. That's my working template. So I've got my list of materials on there. If anything had a 0 on it, it's because it didn't apply to that specific mix. But in 20 minutes, I'd have loved to have gone into 3 or 4 more topics. But, you know. Pardon me?
You haven't experience on
Yes, sir. Yes, sir. We use a medium coarse lightweight aggregate, but we have had sand placed in there for lightweights down into the 80-pound per cubic foot range. The coarse aggregates take us about 110. To go much beyond that and have it placer friendly, it does take some of the fine aggregate lightweights.
and permanent building goes down.
I haven't tested that. I haven't tested lightweight, but I would sure appreciate any hints for that kind of thing. Thank you.
Well, terrific. Well, BJ, thank you very much. Terrific presentation. I'm sure you'll answer other questions.